step down the path of quantum mechanics and quantum physics and talking about the wave-particle duality that is created through quantum mechanics. And there's three main players in this story. Max Planck, fine-looking guy on the left here. Albert Einstein, gentleman in the middle you might recognize. And Louis de Broglie, French guy who actually came up with some pretty cool ideas. So first let's talk about Max Planck. We did this briefly the other day. Using the black body radiation curve, he came up with the idea that energy comes in discrete amounts of energy, little packets called quanta. And he also, in order to make his equation work for the black body radiation, the energy of a photon, or energy needs to come in a little packet equal to h, which is Planck's constant, times the frequency of that little packet. At this point, Max Planck did not believe he had stepped up, or he had discovered anything revolutionary. He still thought it was that there should be a classical explanation to the black body radiation curve. He just thought he had found some sort of a mathematical trick that worked, but wasn't really explaining what's going on. Okay? But then Einstein comes along a few years later, and he says, well, wait a minute. Maybe it isn't a mathematical trick. Maybe it is reality. Maybe on a small scale, things really do come in discrete quantities. And if that's the case, maybe light is that way. And up to this point, people had believed that light was a wave, because we'd seen refraction, we'd seen diffraction, we'd done the double slit experiment to prove it had wave nature, we'd measured the wavelengths of light. Everyone assumed light was a wave at this point. But Einstein says, hey, well, if this quanta idea is true, maybe it's a particle. And in 1905, from the quantum hypothesis, he said that maybe the energy of light comes in discrete quantities, n being an integer, 1, 2, 3, 4, 5, and so on, times hf, so that light basically should come in these little packets. And he gave them a name. He called them photons. And he said each photon would have an energy equal to Planck's constant times the frequency of that photon of light. So this kind of reinvigorated this classical argument of whether or not light is a particle or a wave, because before we had measured the wavelengths of light and Young had done his double slit experiment, there was this argument for hundreds of years. Is light a particle or is it a wave? Is it a bunch of little tiny things or is it just a wave? And in the early 1900s, we thought it was a wave. But Einstein said, well, you know what? We can test this theory. Using the photoelectric effect, we can test whether or not light is a wave or a particle. And if it's a particle, there's something we can do using the photoelectric effect to prove it. For this, he won his Nobel Prize. Now, you guys have just been playing with the photoelectric effect, so you are perfect experts in it right now. And again, I'll show you a little picture of the idea here. You shine light on a piece of metal, and in some instances, electrons will be ejected from that metal. And if you have a little vacuum tube with that photo surface, and you have a collecting surface, and you create an electrical circuit, you can put an ammeter on it. And when electrons are ejected, you'll get a current through that circuit. This is called what is that thing called? It's called something. That's a, it's not the photoelectric effect is the effect of the electrons being ejected. This is like a photo tube or photo multiplier tube or something like that. I don't know. It doesn't matter what it's called. Here's what Einstein said. Using this tool, we would get two different results if light were a wave and if light were a particle. Let's review wave nature for a second. When we studied mechanical waves, particularly, well, this is true for transverse or longitudinal, but remember when we studied waves, the wavelength, the distance from crest to crest, just was, why is that not working? Okay, just was the wavelength. And for light, for example, that just changed the color of light. For sound, that just changes the pitch of the sound. It was the amplitude of the wave, remember measured from equilibrium to the top, it's the amplitude that determines how much energy a mechanical wave carries. Okay? For sound, if I change the amplitude, that's like changing the intensity of the sound, making it louder. And it carries more energy because it has more amplitude. For light, if I turn the light up brighter, and light is a wave, what I should be doing is changing the amplitude of that wave and giving the light more energy, okay? But Einstein says, wait a minute, maybe light's not a wave, maybe it's a particle. And if it's a particle, okay, well, hold on. If it's a wave, let's go with this way, okay? Increasing the intensity should increase the energy of the electrons that are shot off, because increasing the intensity of the wave would be increasing the amplitude, therefore giving the electrons more energy. The frequency of the light shouldn't affect the energy that the electrons have, because in wave theory, frequency doesn't have anything to do with the energy that those waves carry. And there should be a slight time lag from when the light hits the surface until the electrons are ejected, because it should take time for those electrons to gain energy from the waves before they have enough energy to launch off of the metal. These are things that you would expect if light is a wave. But Einstein said, hey, wait a minute, what if light's a particle? If light's a particle, okay, a photon, then I would expect that increasing the intensity would just eject more electrons from the surface, but they would all have the same kinetic energy. Changing the intensity wouldn't change the kinetic energy of the electrons. Because his theory is this: if light's a particle, then when a photon hits those electrons, one electron can absorb one photon. You with me? And so there'll be a direct relationship between the photons and the electrons that are ejected. If I increase the frequency of the light, then I should be increasing the energy of the light, and therefore the energy of the electrons, if light's a particle. Because remember, he said that if light's a particle, the photons will carry energy equal, gosh, these pens are not working very, equal, energy is equal to h times the frequency. I give up. I did. I think that's a potential possibility. We could do that too. Okay, and at some frequency, I can turn it down the frequency. So at some point, the photons don't have enough energy to knock off any electrons, no matter how intense. It's like the ping pong ball with the bowling pin analogy. If my photons don't have enough energy to eject electrons, it doesn't matter how many photons I shoot at that metal, no electrons are coming off. That's true if light is a particle. If light's a wave, however, if I go low frequency, as long as I wait long enough, it'll eventually build up enough energy to eject electrons. That would be the prediction. Okay, so this was his theory. Again, Einstein was a theoretical physicist and not an experimental physicist. But in 1913 and 1914, Robert A. Millikan conducted some experiments to test the photoelectric effect, and this is what he found. This is what he found, okay? He noticed that if he changed the frequency of light, the stopping potential, that's what you guys did by adjusting the voltage. You can measure the energy of the electrons by switching the voltage so that when the electrons are shot off, they're swimming upstream. They're working against the electrical field. And by adjusting the voltage, you can turn that voltage up until no electrons make it. And that is what's called the stopping potential. And the stopping potential tells you how much energy those electrons have, because they'll only make it up until a certain point. So he was able to measure the energy of the electrons relative to the frequency of light hitting the metal, and he noticed there was a perfectly linear relationship that as the frequency increased, the energy of the electrons increased linearly, exactly as predicted by the photon theory of light. And below a certain frequency, no electrons were ejected. This is for a given metal, B. Notice that a given metal, A, looks exactly the same, but it has a different threshold frequency. There's a different amount of energy needed to knock those electrons off. The slope is identical, okay? The slope will equal Planck's constant, okay? So this is the evidence that came up. We use this photoelectric effect all the time now in burglar alarms and smoke detectors and all sorts of things. Here's the equation that will be helpful for us. I don't know. But okay. The maximum kinetic energy that the electrons will have is equal to the energy of the photon, HF, minus the amount of energy it took to release the electron from the metal. That's called the work function, okay? I believe this is the equation that's in your data booklet, and it's one that will be useful to you, okay? The work function is how much energy is needed to release the metal. And you can get that work function from this, right? This frequency is known as the critical frequency, and if I multiply that by Planck's constant, that is the work function. That's how much energy it took to release that electron. Okay?
Is the work function in joules?
All right, let's try this. So here's a stopping potential of 4 volts. Okay, stopping potential of 4 volts. That's how much voltage stops the electrons from making it across. What is the kinetic energy given to the electrons by the light, both electron volts and joules? This is one of those questions where the first part you should be able to answer in about 7.5 seconds. Okay? Does that make sense? Everybody clear on that? Stopping voltage, what we're talking about? Okay? Here's the work function for cesium, 1.96 electron volts. Find the threshold wavelength, which can also be found from the threshold frequency. We were just talking about that a second ago, right? For cesium. But you know the answers. We can work on it. We can work on it. But right now I want to keep moving because we're going to run out of time here. Now, the Compton effect. The Compton effect, okay? Yeah. In 1923, this physicist A.H. Compton, he took X-rays and he bounced them off of things just to see if X-rays would also follow the photon theory of light. And according to photon theory, when he did this, the frequency should change depending on the angle that the X-rays were deflected. And when he took measurements, they were in total agreement. So this was really just, what you need to know basically is the Compton effect was another experiment that showed that light, electromagnetic waves, can also be particles, okay? So 2 pieces of evidence that support the photon theory of light is the photoelectric effect and the Compton effect. And we've got equations here about momentum now. So momentum equals hf over c, or h over wavelength. And so suddenly we can calculate the momentum of these little photons, these little things. Even though they don't have mass, they can still have momentum, which is kind of crazy, but they do. So now we have all this evidence that light comes in these little packets that we call photons. There's the Compton effect, okay? There is the photoelectric effect. In the photoelectric effect, the photon is totally absorbed, and the electron is released. Energy conservation tells us what will happen. It does. Okay? If the photon doesn't have enough energy, if the frequency is not high enough, or if the wavelength is not small enough, then basically instead of knocking the electron off the metal, it'll knock it into one of its excited states and then drop back down and give off another photon. So the photons are absorbed by the electrons, but they can also be released by the electrons. Okay?
So what's the difference between the photoelectric effect and the Compton effect?
Here's another crazy thing about the photon idea of light, is that you can take energy, remember E equals mc squared, you can take energy and turn it into material, turn it into matter. But in order for this to happen, you get pairs of particles, pair production. So this is how antimatter and matter get created. You can't create matter without creating antimatter as well. And so if you have enough energy, you'll get an electron and a positron, for example, but you won't just get an electron. And the photon will disappear. So here we have energy turning into matter, matter turning back into energy. And so here's what we're getting now. Ooh, look at that. There's a picture of matter and antimatter being created from a photon, from energy, okay? E equals mc squared, okay? And so here's what we're getting at. Here's where things start to get kind of weird. All of these experiments are showing us that light is both a wave and a particle. Sometimes it acts like a wave, sometimes it acts like a particle. And we have experimental evidence proving both, okay? We had the double slit experiment where we shone light through 2 openings and it created an interference pattern because of diffraction. That proved that light was a wave because particles just won't do that. The fact that light refracts tells us that it has a wave nature, okay? And diffracts. But now we have other experiments, the photoelectric effect, the Compton effect, that are showing us that light also acts like a particle. And it does both. So we can't ignore either of them. So suddenly we have this description of electromagnetic radiation as being a wave and a particle. And we call it the wave-particle duality, okay? And the way it behaves is determined oftentimes by the way you interact with it, the way you observe it, all right? Now, Louis de Broglie, this is awesome, I think. He's like, well, cool. If what we used to think was, he says, hey, if what we used to think of as being a wave also acts like a particle, what about the things that we think of as being particles? Maybe they act like waves. And he came up with a mathematical equation to express the wavelength of anything. You, me, baseballs, airplanes, wombats, we can figure out their wavelengths, okay? And it's a simple equation. You take Planck's constant and you divide it by the momentum of the object, and that will tell you the wavelength of its wave nature. It's known as the de Broglie wavelength. Notice that, first of all, is H a big number or a small number? Isn't it 10 to the negative 34th? Very small number. Okay, remember talking quantum mechanics is very small. If I take a very small number and I divide it by something that has a very large momentum, what do I get? Even smaller. So you have a wave nature. You are a wave. But your wavelength is so small, we can't measure it. We don't notice it. We don't see it. But if you have a small enough object like an electron, electrons, classically we've thought about electrons as being these little particles orbiting around the nucleus. But according to quantum mechanics, not only is an electron a particle, it must also be a wave. And we can calculate its wavelength. And perhaps we could even measure its wavelength. And in 1927, Davison and Garner, they took electrons and they scattered them off of crystals, and they measured the wavelength and the diffraction pattern. And they got electrons, these things that we thought were particles. They got them to make diffraction patterns to show that, yes, they are also waves. So what this tells us is that everything is both a particle and a wave. Brian. So here's kind of a typical physics question where you could calculate the wavelength of an electron. Now, an electron doesn't just have a wavelength that stays constant. Remember, the wavelength is determined by the momentum of the object. So what I would do for this equation, since we don't have a whole lot of time, we'll just kind of run through this. If I can figure out how fast that electron accelerates by the voltage, the potential difference, and I know its mass, I can figure out its momentum after it's accelerated through 75 volts. Once I know its momentum, I can find its wavelength. That's kind of how you do it, okay? The speed, well, remember that that potential difference, or voltage, is energy divided by charge. So I could find out it'll have 75 electron volts of kinetic energy, and then I could find its momentum from that. Okay, and that would be the answer I would get. Now notice, even something as small as an electron, its wave nature is still incredibly small. Your wave nature is so small that we really can't measure it. Like it would be impossible. It would be a wavelength beyond gamma ray. I mean, it's like teeny, tiny, tiny. But theoretically, we could calculate it. Okay. The wombats is pretty darn big. Now, is that a wombat standing still or a wombat running and attacking its archenemy, the platypus? That's a wombat.